So good afternoon, everyone, and welcome to the fourth physics colloquium lecture of this season. And today we are really very fortunate to have very distinguished the researcher of our Indian soil, Professor Jayanta Bhattacharjee from Indian Association of Cultivation of Science. And he didn't need much introduction for the people who knows him because he has inspired a great bunch of students to pursue in the research through his lectures and through organizing schools. And in the scientific community, he is quite well known for his grand contribution in the field of instabilities and turbulence. So, for the sake of the young student, I would like to say a few words about Professor Bhattacharjee. Professor Bhattacharjee completed his PhD from University of Maryland in 1979, and then after doing couple of postdocs, one from University of California, Santa Barbara, and another one from Germany. He joined IIT Kanpur in 1982 as an assistant professor. He remained in IIT Kanpur until 1995. After that, he moved to IACS, Indian Association of Cultivation Science, and he remained there until 2007. And from 2007 to 2012, he was associated with SN Bose Center for Basic Science. In 2012, he took a charge of director of Horizon Research Institute, and there he remained until 2017. And after that, he joined IACS as a emeritus distinguished professor, and so far he is affiliated with until now he is affiliated with that institute. His research interest lies in hydrodynamic instability and turbulence, critical phenomena, chaos, and many other fields that you can basically get after going to through his website. And he has written very classic books also in physics, and some of his famous books are the nonlinear dynamics, near and far equilibrium, convection and chaos in fluids, and equilibrium statistical physics book, which is quite popular among the MS masters and research student, that is statistical mechanics, equilibrium, non-equilibrium aspect. So also he has been awarded for many awards, and just few to mention that he has received Fellow of Indian Academy of Science, Bangalore. He is Fellow of National Academy of Science, Allahabad, and many more. So I will not basically take much time now, and with this, once again, I would like to welcome Professor Bhattacharjee to deliver today's physics colloquium on dynamical system, turbulence, and active matter. And I hope you will enjoy the lecture. So with this, I hand over the forum to Professor Bhattacharjee.
Okay. All right. So can you see this slide?
Yes.
All right. So let's get started. I would certainly like to thank Saurabh Basu and Pankaj Mishra very much for arranging this lecture. And actually, it is a pleasure to talk about turbulence in IIT Guwahati because a fair number of interesting results have come out of there, courtesy Malay Nandi and Pankaj Mishra among the faculty members, and a graduate student, Tapash Singha, who wrote one of a rather interesting paper on skewness in Kolmogorov turbulence. So that was actually very interesting. And so with that, let's get started. I'll try to be non-technical, but sometimes things may look a little mathsy or whatever, but don't worry. I mean, if you don't, you can be blind to the maths. So, all right, we start with what turbulence means. Turbulence is essentially a very complicated kind of fluid motion, complicated in the sense that you cannot characterize it by a definite pattern. It's not like normal course, a river flowing by. You have more or less steady velocity and maybe some ripples on its surface. But here, and you can actually write down what the velocity is at any point of the fluid at any given instant of time. You wouldn't have a problem with that. The turbulent flow is when you cannot do that. What happens is that at every instant, the velocity vector changes at any given point of space. And similarly, at any given point in time, if you take a snapshot, you would find a rather irregular distribution of the velocity field. A particular example is stirring your coffee. If you are not very careful about stirring it at a uniform rotational speed and so on and so forth, you'll find that the swirling motion really has no particular characteristic feature. So what has become very clear, what everybody agrees on, is that this is a system where this turbulence is driven by nonlinear terms. So that's where nobody quarrels with anybody. You agree that, so that's the one fact which is uncontested. So we go to the next one. I need to bring you what is the basic dynamics of fluid motion. That it has to be, it is classical, so there has to be a Newton's law to it. And Newton's law means that I need to be able to write acceleration on one side, which is the left-hand side over here, and forces on the other side, which is the right-hand side over here. So the forces I need to talk about for a couple of minutes. The first force that you see over here on the right-hand side is the pressure gradient. The next is the viscous dissipation, which would eventually cause motion to stop if there was nothing else going on. And this is any applied force that one can have. For example, if it was the stirring coffee, it is the stirring force that you introduce. If it is a buoyancy-driven situation, then it is your good old gravity, and so on and so forth. So now we see that here is a linear term, here is a nonlinear term, here is a linear term, here is a term which has nothing to do with linearity or nonlinearity, and this, mind you, is a nonlinear term because which you can very easily see, we'll be talking about an incompressible fluid, which is not at all a bad approximation most of the time. And in an incompressible fluid, I can take the divergence of this equation, and the divergence of this gets related. So this vanishes, and you have the del square of P becoming the divergence of this. So P is essentially a nonlinear function of this quantity over here, which is like this quantity over here. So P is a nonlinear term which is in the same, which is at the same footing as this v dot grad. So all right, so how big are the various terms? If a characteristic velocity is capital V, then this term has two V's and one L in the, so it's V square over L. This, so is this, and this one over here is eta, the viscosity coefficient, times V, the velocity, over L square, because there are two L's in the, so ratio of the nonlinear to the linear term is this dimensionless Reynolds number, which is VL over eta, and nonlinear means that the nonlinear term has to win, and therefore the Reynolds number has to be very big. So turbulence is when Reynolds number is very big. All right, so what is the next thing is that what is the primary characteristic? The primary characteristic is that I cannot write down for V of R and T a standard function of space and time. So the velocity variable is unfortunately a random function of space and time, and that is what makes life so difficult. Well, all right, so what is a characteristic of a random process? The process which all of you are familiar with is diffusion. What does diffusion tell you? It tells you that x squared is like t. So x squared is, so what is being violated is the familiar statement that between two neighboring time intervals, t plus time points, t plus tau and t, this difference is generally of the order of tau, which is this dt over here. So this small difference would be like proportional to tau. Diffusion tells you x squared proportional to t. So this difference over here is no longer proportional to tau, but it has a square root of tau behavior. That is what, if you are in statistics and so on, the Ito calculus is all about, and the analog is going to exist in turbulence. And here is the standard picture, the picture which Pankaj used for the announcement of the talk. And what you see is what a turbulent fluid looks like. And the important thing to see, which is going to be the vital point for a long, long time of this talk, is that look at the circular pattern. There is a large one over here, and inside there are the smaller ones. And you look at every scale, there are these vortices. So you see so if you look at, take any vortex, inside it there are more vortices, and more vortices, and take any one of them and magnify them, and you will still see more vortices and vortices and vortices. Take the smallest one, magnify it, and you will see the same picture. And that is what scale invariance is all about. And scale invariance is what we will be looking at. So, all right, the particle diffusion and the analog. So now, here is the particle diffusion answer, which all of you are familiar with, that the mean squared displacement is proportional to tau. So after a time tau, you look at the mean, it's proportional to. So now the analog exists in the steady turbulent flow. Steady flow is, we will not, it is dynamics, but we'll be talking about a steady flow. So what is steady in dynamics? What is steady in dynamics is that in this dynamics over here, the fluid is evolving, and at any given point, there would be, the velocity field would be something right now. It could be something else a little later, something else sometime later. And what these what this set of fluid velocities at different times are going to be is that they are going to be this having a probability, the characteristic of the turbulent flow is that they'll have a probability distribution, and you will have to talk about average values. The averaging, it is average values which one talks about, and what one means by steady state turbulence is that the average values are independent of time. The probability distribution that takes care of things, or is supposed to take care of things, and you are supposed to find it, is time independent in the steady state turbulence. And so what the analog of this particle diffusion is a question of space rather than time. So you look at two neighboring points and you ask for the velocity difference between those 2 points, and the velocity field, the square of the velocity field, difference squared, and take the average, and that is proportional for very small values of r to r to the power 2/3, and there is a constant of proportionality here, which I have called k, to remind you that this is the result which was obtained by Kolmogorov. So this is the kind of result that one is after, the kind of result that you see in this line, that it is a question about the distribution of the velocity field. The turbulence is characterized by a random distribution of the velocity field. The random distribution would have the underlying probability distribution is what you are after and what you will not get. So, all right, the vorticity, Da Vinci focuses on that. I just showed you the picture. We'll not talk about it anymore. We'll go straight to what are we going to talk about. As I said, that we are going to talk about the velocity field, which is a random function of space, and it is the time average things which we'll be talking about. There will be no boundary conditions, and what we want to talk about is the underlying distribution function. What is the probability of having a velocity v of r at the point r? And that is the thing which is almost impossible to obtain, and therefore will settle for a much more an infinitely more restricted viewpoint. Just tell me what the 2-point correlation function is. That is, I go back, what we did a minute before, that here is the correlation between what's happening at x plus r and what is happening over x. That is what I mean by a 2-point correlation, and it is this 2-point correlation in coordinate space or the Fourier space, which is often easier to work with, that we'll be talking about. So once again, the starting point is the fluid equation, which you are familiar with, and from the slide before. And I have now put in explicitly the divergence free condition. Repeated indices are summed over and so on. And let's talk about the first quadratic quantity, the v square, the kinetic energy. I should have put a factor of 2 over here. But anyway, since it does not matter, it's missing, but it should have been there. So the average kinetic energy of the flow, you take your v square at a particular point and you integrate over all space, divide out by the volume v. That is the average kinetic energy, and this is per unit mass, and this is what we call E. In momentum space, here is, Parseval's theorem at work. You take v square r d3r, write the Fourier transforms, and it is vk, v minus k, integrated now over the momentum space. So d3r goes to d3k, v of r times v of r goes to v of k times v minus k. And in this, I can write the way to write this is to write it as an integral ek dk. So you have integrated out the angles and things like that. And what you are saying is that here is my total energy over here. And here is the energy which, this total energy is distributed over all wave numbers, and I'm just looking at the amount of energy which is contained between k, wave number k, and k plus dk. That amount of energy is this ek over here, and ek integrated over all k gives me the total energy. The point is, the absolute minimum requirement of turbulence is that find this E of k. So I have a turbulent fluid, I have this random function of space and time. There is a certain amount of energy associated with this fluid, and all that I'm asking is a very small question, that how is this energy distributed among the wave vectors. So that is the question that one asks and tries to understand at the most basic level. So all right, it is the energy, right? And therefore, what will you do? You will integrate this, you will multiply by V alpha over here, and that is this equation, and integrate over all space, so that this term over here is the time rate of change of energy. So time rate of change of energy, when I multiply by V alpha and integrate, if I multiply by V alpha and integrate, because of this, the integral is 0. Similarly, over here, the integral is 0. And what you have when I do this integration, you have a couple of terms left. On the left-hand side, you have del E del t, and on the right-hand side, you have this. And you see what has happened, the great simplification, your nonlinear terms have just disappeared. You have, when I'm talking about this rate of change of total energy of the system, I'm left with just two terms on the right-hand side. One, which talks about how much energy, this is the external force, and this is the rate of work done by the external force. So this is the amount of energy I'm inputting to the system, and here is the viscosity dissipating it. So it is the energy equation is, because of the incompressibility, is amazingly simple. The total energy, this is the total energy, mind you, the total energy, if I did not have any external forcing, would just go to 0 as time goes on. Motion would come to a stop because of viscosity, which is natural. And if I did not have any viscosity in the system, it would just, the energy would keep on increasing, so the velocity would increase without bound, which is unphysical. So you need to have viscosity, and if you want to maintain the flow, you have to have an external flow. All right, now what are the scales? See, look at this. This has a 1 over, this is ddx over here, and it's squared. So ddx, it gives a length scale in the denominator. So this would be big if the length scale is small. And therefore, at small scales, which is the small l, this term dominates. And the input, that is, for example, when you are stirring your coffee cup, you stir along the sides, and you are putting in energy over this large scale, which is the diameter of the cup. So here is the input energy coming from the term over here, which is occurring at a scale which is capital L, which is more or less a typical system size. And the rate, you assume that you are putting in energy at the constant rate which is this epsilon. So what do I have? If I have a non-equilibrium steady state, that is, the total energy is neither increasing nor decreasing. So that is what is called a non-equilibrium steady state, NESS, as is commonly called the NESS. So you have this non-equilibrium steady state, and the non-equilibrium steady state has the input energy epsilon control equal to the dissipation energy. So that is what gives rise to this non-equilibrium steady state, and this holds as viscosity goes to zero. So even if viscosity goes to zero, and that means that as the viscosity becomes smaller and smaller over here, this has to become larger, which means that the derivative becomes singular, and therefore there is non-analyticity of the velocity field. So that is what the Kolmogorov theory of turbulence is all about. The slide which I showed you in the very beginning, that V minus some delta V square going as r to the power 2 by 3 is a statement about the non-analyticity of the velocity field, and that is what you see over here. So non-analyticity of the velocity field, the hallmark of turbulence, and you can sort of get an idea of it. So now these two small scales, one small, one big. So if I look at the small scale, it has epsilon, which is the rate at which energy is being fed into the system, has to be everywhere. I mean, it has to play a part in the dissipation, it has to play a part in the injection. So injection or dissipation, it is always there. And if it is dissipation, the other chap who is important is the viscosity, which is this, I should have written a mu, sorry, and the L is determined by this, the small scale is determined by this, whereas the large scale is determined by this over here. So the Reynolds, it is the Reynolds number, and take the ratio. If you take the ratio of the large scale to the small scale, that's Reynolds number to the 3/4. So that is the big answer, number one, that the two length scales which I talked about, the large scale and the small scale, are separated by Reynolds number to the 3/4. And so if Reynolds number is very high, these scales are very, very far away from each other. So that's the big question. So that's the question, that what does that lead to? So what it leads to is a range. Now, all right. So this is what I need to drive home. Small l is the viscous scale, and therefore depends upon what the viscosity of the fluid is. It is going to be, if it is pitch is the liquid, it's going to be one kind, water another kind. If it is air, it's going to be another kind. So small l is going to depend on the system, and if it is capital L, that is the large scale, it depends on what kind, whether I'm taking a small beaker or large beaker, or whether I'm talking about a tank, or whether I'm talking about this or that, and so on, and what is the amount of stirring that I'm doing. So this is what is going on this is what is going on over here. And if these two scales are very far separated, for example, by orders of magnitude, let's say 6 orders of magnitude, then I can imagine that in between these scales is a set of length scales which do not know what fluid it is, or what the way of whether I'm using a small pump to inject energy in the system, or whether I'm using a spoon to inject energy. That the intermediate scales here do not know. And therefore you can see something about to happen, that things which happen in the middle range, which goes by the name of inertial range, and that inertial range is universal. It does not depend on what fluid I use. It does not depend upon how I inject energy into the system. So the picture that Kolmogorov generated is that if I look at this energy, the total energy of the system, it is increasing because there is something happening at large scale. I'm pumping energy into the system. It is decreasing because the viscosity is taking part in it at the short scales. But in between, there is nothing happening, neither dissipation nor production, and therefore the energy created at large scales to be dissipated at small scales, the energy has to just flow through the scales without any loss. So that was the picture of that Kolmogorov had, that if I put in energy at the rate epsilon that you see over here, so this is the rate at which you are putting in energy, this is the rate at which you are losing energy, one happening over here and the other happening over here, but through this middle range over here, the epsilon just passes without any loss from the large scale to the. So this range over here through which there is a lossless propagation of energy is the so-called inertial range. And in the inertial range, says Kolmogorov, the energy spectrum which we defined in this manner is going to be determined only by k and epsilon. K, obviously, because it is a function E of k, and epsilon, because obviously if there is a large amount of energy flowing, E will be bigger, and if there's a small amount, then it's going to be smaller, and therefore this epsilon has, and now I can do a dimensional analysis. And I'll leave you to do the dimensional analysis and figure this and get this out. Just remember, the dimensions are that of L, length, and the mass has been set equal to 1. So it is length, which is capital L, time, which is, let's say, capital T. So those are the only two quantities. And K, which is inverse of length, is therefore like 1 over L. And rate of energy supply, energy is L square over T square. The rate is L square over T cube. And from here you see Ek has the dimension. This Ek over here has the dimension L square over T square over here, 1 over L over here. So dimension is L cubed over T square, and you have to fit L cubed over T square to epsilon to some power and K to some power. Get two equations for capital L and capital T. Out will come this. And this is and similarly, if you do it for velocity difference raised to the power n, there it depends on r and on epsilon, and you should be able to pick up the fact that if it is raised to the power n, then this difference goes as r n by 3. So if you put n equal to 2, it is the n equal to 2, r equal to r to the power 2/3, which I talked about. So here is the bottom line, that you have a universal answer. It is E of k, regardless of how you are forcing the fluid or what fluid you are forcing, it is k to the power minus 5 by 3. What's more interesting, so that's one part. And this, I mean, by now, there is absolutely no doubt that it is k to the power minus 5 by 3. And the corrections which there could very well are so small that it will take a few more generations to find a correct of computer sophistication to get that. But 5/3 is as good as it gets. That was the pure and simple dimensional argument of. But this number C, that is also a universal number. And Kolmogorov was 1941, so that's 8 years ago. And while this 5/3 is, let's say, reasonably well understood and agreed upon by more or less everybody, the C, it's a universal number, nobody would question that, but it has a value, and nobody, where there are various schemes for calculating it, and nobody trusts another person's scheme, and for good reason. The problem you see is right over here. So here, everything is happening for us in turbulence in this middle range. If you were a condensed matter person, it would be for the condensed matter person, the requirement would be that you look at collective behavior. The only interesting behavior in condensed matter is collective behavior, and collective behavior happens over the large length scale. If you are a high energy physicist, it is the high energy behavior, and that happens at small length scales. So the condensed matter guys live over here, the high energy people live on this side over here, and you can use renormalization group for both ends. So the renormalization group works over here as started out by Wilson. That's the critical phenomena and subsequent all kinds of collective behavior. Over here, it is the asymptotic freedom, which was Gross-Wilczek and who was so high energy people with when it works with this asymptotic freedom. They live over here. They live over here. The turbulence people live over here, and therefore you have a theoretical problem. You try to bypass that by doing this or doing that. But if you do this, then there is one community who would always be there. If you do that, there would always be one community who can challenge what you do. So that is what is. And as for, here is the numerics. This is to show the 5/3 thing works. This is more than a decade back when the size of the system was 1024 cubed. Today, Pankaj, I'm sure, does it certainly at 4096. There could be people who would be at 8192. And the point is that the 5/3 is not doubted. So, all right. So now, lest you think that this was all linear physics, what did the nonlinear term do? The in momentum space, here is the nonlinear term, this one over here. And what it does, it's the nonlinear term which actually moves energy from one scale to another. So this is the vital thing. This is the so-called transfer term, and the transfer takes place from one scale to another in such a manner that this E dot K is actually K independent. So that is the whole business. Kolmogorov just said it is K independent. It is up to the later generation to show it is K independent. And somebody who has spent a large amount of his time actually investigating the scale independence of this E dot K over here is Pankaj's thesis advisor, Mahendra Verma, who certainly is responsible for a huge amount of very important results in the scale-free nature of this. But all right, so that is the turbulence picture. So isotropic, homogeneous turbulence. That is what you need to know. If you have got some significant part of it. But the point is that, all right, I mean, that is all very, but the in question, this was 1941, and immediately thereafter, after this Kolmogorov thing, Landau asked the question that how in the world does this thing set in? You look at the flow, you start increasing the Reynolds number, and does it happen that a flow which is taking place, let's say, at constant velocity down a channel, if I increase the Reynolds number, does it immediately become turbulent? And the answer is no. It has to go through a sequence of steps. And therefore, the Landau and Hopf came up with a feature that, look, they said, if I increase the Reynolds number, first it is a steady flow with no periodicity, just constant velocity flow. Then if I increase it a little more, the Reynolds number a little more, then it would be a flow which would become oscillatory, characterized by one frequency. If I increase it a little more, and then there would be a second frequency incommensurate with this coming in, and then when it is the Kolmogorov variety, that would be a whole slew of incommensurate frequencies, which is noise-like, and that was the Landau-Hopf way of turbulence setting in. But that was not, nobody actually saw it in real life. And then came the 70s and the theorem, which says that almost after two frequencies, you set in to a very complicated thing. So you want a better way of better setup for this kind of stuff. And the better setup is to look for hydrodynamic instabilities. So hydrodynamic instabilities are supposed to lead to something called chaos. Chaos is different from turbulence in that there is a sequencing. Sequence is that you have a steady flow, and then if you change something which is like a Reynolds number, and you will see a time-dependent flow, and then more complicated time dependence, and then finally time dependence which is completely disordered, but the spatial pattern is not. You still have some spatial pattern, but the time series is completely disordered, and that is what is meant by a chaotic solution. A chaotic solution is characterized by an infinite set of incommensurate frequencies. All the frequencies are there. It is not just omega 0, 2 omega 0, 3 omega 0. It is omega 0 and omega 1 being not a multiple of any kind of omega, that is not rationally related to omega 0. Then there is a omega 2, which again, and this. And so therefore, if you look at the frequency spectrum of the time series, it has all, it has a contribution at every frequency. That's chaos. And turbulence go from here to here through disordering in space as well. So the point was that, all right, let's look at chaos, and let's, if I want a physical system, then a physical system would be one which shows hydrodynamic instabilities, and let's go to chaos and then see what to do with turbulence. So here and there comes the system where Pankaj did a lot of work at IITK, and it is a system where you take a layer of fluid and heat it from below, so that heating it from below is potentially, it's a static layer of fluid which you heat from below, and if you start, if the temperature gradient becomes rather big, then hot liquid will start rising, the low cool liquid from the top will fall, and you would have a circulation. So you are supposed to see a sequence of this kind experimentally, a steady state with no motion, and then a steady convective thing where convection is set in and is steady, and then becomes oscillatory, and then it becomes chaotic, and then turbulent. So that's the experimental sequence that you want to explore, and the numerics. So the governing equations change a bit. It becomes a little more complicated because now it's a buoyancy. You have to include gravity. So there is gravity. The system is anisotropic. There is gravity in this, and you also have to worry about the temperature. The temperature follows a diffusion equation. Here is the ddt, which ddt has a partial derivative and the u dot grad, and so on. And so forget about all this. This is to, for those of you who know, it is just to sort of remind you. And for those who are not familiar with it, don't even worry. It is that I have a situation where I take a layer of fluid, heat it from below, and it is under gravity, and gravity shows up in the fluid mechanics. Temperature is also a variable, and the control, the parameter which controls things is the expansion coefficient times the temperature difference, acceleration due to it. So there's a dimensionless parameter which one calls Rayleigh number, and the convection sets in at this 1708. So what happens if you do experiments? You do see convection setting in over here, steady convection at R equal to RC. You go to a little higher R, and you will see let's say I have a steady set of convection rolls, and then the axis of the rolls start wiggling. So you have wiggling rolls, and then the time with a single period, and then as this small r is varied, you have more complicated time dependence, and so on. While all this was going on, these experiments certainly looked pretty promising, and numerical simulations also. While all this was going on, there came a big spurt of knowledge in dynamical systems, and the point over there was that you could, if you started looking at, instead of differential equations, if you started looking at maps instead of differential equations, that is discrete versions of the differential, not a continuous time thing, but let's say I have a variable x. If it is x of t, I look at x of t plus delta t. If it is a discretized system, then I look at the nth point, I look at xn, and then I go to n plus 1, and I look at xn plus 1. xn plus 1 as a function of xn is what is called a map. So this map became the nice thing to study. And the very interesting thing about maps was that a nonlinear map showed period doubling. That is, a map after, let's say, a large number of iterations. Let's take a map between 0 and 1. It's like x into 1 minus xn into 1 minus xn. So n plus 1 at iterate, xn plus 1 is some r, the control, xn into 1 minus xn. So you go give a xn, and now it is very easy to see that if I go on, start with it's all of this is between 0 and 1. And if I go start with some point between 0 and 1, if r is under 3, I will eventually end up at a fixed point. If r exceeds 3, you will find that the fixed point breaks into 2 points, and you end up with a cycle that is a set of 2 points, x1 and x2. x1, operate the map, you go to x2, operate the map, back to x1, and then x2. And then if you increase it still further, then it is x1, x2, x3, x4. And the way it works is x1 goes to x2, goes to x3, goes to x4, and you are back to x1. And this repeats. So you had a period 2, now you see a period 4, and then you see a period 8, and so on, which is called a period doubling. So the end of the 70s saw this emergence of period doubling, and period doubling eventually led to quote unquote chaos. There is eventually, when the period became infinite, you would not be having any periodic trajectory. It is not exactly a chaotic trajectory because you don't have all the incommensurate frequencies, but that's a small point. Let's not get lost on that. The important thing was that there was this period doubling, and that essentially took you to from periodic states less from period t to period 2t to 4t to 8t, and then no period, which looks like chaos. And then the point was, can you, the experiments that one did with the fluid, will they show this thing? And the point was that it never did, that it did not. There were a couple of situations in the early 80s when a couple of experimentalists with a lot of hard work, or more important, lot of luck in addition to hard work, saw period 2 and period 4 and period 8, but then thereafter they never saw the sequence anymore. But what about theorists? What if I start with the PD that I showed you a few slides ago and try to analyze the PD? Analyzing a PD is no joke. But then Lorenz, way back in 63, found a way of analyzing the PDE by changing it to a set of coupled ODEs. What you do is you focus on a few modes which capture the physics. And then you just use those modes alone, and the coefficients of those modes are time dependent, and in that time dependent, through that time dependence come the ODEs. So here is the most famous ODE really of this variety, which was written down in 1963 by Lorenz. And one thought, aha, what would this Lorenz model show? What would it show? A set of a characterization of chaos through some exotic route? And the answer was no. There was a trivial fixed point, that is all at zero, that's your steady state, going to another constant fixed point, which is non-trivial, and that being destabilized through a hop, so a formation of a periodic state, but that periodic state never actually is seen in a numerical simulation of the Lorenz model. So the Lorenz model was a very nice start of looking at PDEs for a theorist and trying to make sense of PDEs. But if you what Lorenz model did was that it took you from fixed points directly to chaos. So this great thing of period doubling bifurcation, which the late 70s, early 80s people, theorists were so fond of, and Lorenz model, which was a paradigm for chaotic behavior, Lorenz model just did not have it, and therefore, once again, a sort of tragic impasse that here you have the theorist's favored route to chaos. What a theorist would love to see, where business was started by somebody named Feigenbaum, who in 1979 found this period doubling route to chaos, that what the theorists would like to see a real situation like the fluid modeled by Lorenz. It starts with reality. The fluid is real. The model is a model, all right, but a model based on reality. And what the theorists would like is a model based on reality, showing you this period doubling, bifurcation, and chaos from that. The tragedy was that none of the Lorenz-like, from the PDE to the Lorenz-like model, never showed the desired sequence. So this was, I mean, what essentially was problem for people, and then enters something called active matter. So so you can imagine I'm at the last 5 or 10 minutes, and the active matter is something which active means that it is matter which has its own source of energy. So what, I mean, it's like bacteria in a fluid which can create which can be a model for this active matter. And what is meant by active? I mean, all these words have. The point is that if I put some inactive matter in a fluid, it just drifts along with the fluid flow. Active matter is capable of actually exerting a stress back on the fluid. It can throw its tentacles around here and there, whatever tentacles back, I mean, you know, whatever structure a bacteria may have. It can throw it around and cause minute stresses on this fluid. So that is what activity means, that you have, instead of salt or sugar or things like that, I mean, particles mixed in a fluid, you have now mixed particles which are actually capable of exerting a stress on the fluid. So this creates a stress, additional stress term in the equation there. And this was popular with who never dreamt of bacteria, but critical phenomena people in the 70s, to which I belong, were very fond of this model, but had never dreamed that one day it would go to this. This was the contribution of, the active matter came, but the fact that this critical phenomenon model would become active matter model was the contribution of Cates, and essentially the driver, Cates was the driver of that, with Tiribocchi, Witkowski, and Marcuso, which was 2015. And what they said was that you are going to have, well, there is the here is the concentration of the bacteria, and this is the same equation as for the temperature field. The bacteria diffuses. This is the d phi dt. This is the concentration of bacteria active matter. This is dd, total derivative over here, total derivative over on this side over here, and it is on the right hand side the diffusion term. And then over here you have the total derivative du dt on the left hand side. On the right, what you see is the stress tensor, derivative of the stress tensor, and there is one term coming from the pressure, there is one term coming from the viscosity, that we have handled before. Now we have an additional term coming from the active matter, and this additional term is related to the gradient of the concentration, and this is what it looks like. I mean, constant gradient, no forces, no, it is when the gradient changes, that is, when the gradient exists, that is the concentration changes, that you have a contribution over here, and this coefficient is called the activity. All right. For the 70s and early 80s people who were doing dynamic critical phenomena with this model, zeta was always equal to unity. And we were used to fluctuation dissipation theorem and so on, which holds only if zeta is equal to 1. Now it is no longer fluctuation. Zeta is now changed. I mean, the bacteria don't follow zeta equal to 1. They can have zeta, I guess, how well you feed the bacteria. They can have different values of zeta, and it is just a number which can change with the kind of bacteria you use. Yes. So, all right, now that makes, so now you play the, so I want to do a setup, which is the analog of the fluid setup with a thermal gradient, except that now I have, imagine that there is a bacteria gradient maintained across the plate. Some clever experimentalist one day would certainly be able to do this, how to maintain a bacteria gradient, which is this S, across two sets of plates, between which there is this fluid in which the bacteria has made its home. So there is the NES, which is the steady state, where you have the bacteria density is a constant, and then there is no feedback from the bacteria, and everything is like ordinary fluid mechanics. But then comes the question of having and then some amount of algebra, but it is what one is driving at is looking at the Rayleigh-Bénard instability, which the equivalent of the Rayleigh-Bénard instability and what happens there, and the question of what if I set up a Lorenz model. So that is what we did a couple of years ago. So this is the Lorenz model which I showed you a little while ago, except that it has one additional term, which is this. So here is, this is the one which, this term is activity driven and has to do with the velocity field being driven by the concentration field, Y and Z are concentration. So this is the additional term that one has. This is the Lorenz model, new Lorenz model that we are talking about. It has all the properties, the Lyapunov functional and so on and so forth. Trajectories are bounded. That's a theorem which can be easily proven. And so there is a trivial fixed point which is destabilized. There is a non-trivial, and this time through a Hopf bifurcation which can actually be seen. So here is the big difference from the previous Lorenz model. We can actually see a periodic state. So when the steady state is destabilized, you actually, the non-trivial steady state, you actually see a periodic state. And this periodic state, what was IITK undergraduate who came to do a project with me a year and a half ago, found this absolutely stunning set of bifurcations that the periodic state starts period doubling and eventually becomes chaotic. This is what the lines that you see over here, this is period 1, period 2, and here is period 1, period 2, and the periods are increasing, and you have a thickness over here, a higher period, and eventually a chaotic trajectory where trajectories are going between one descent and descent and arbitrarily flipping from one side to another, and you have a chaotic state. So you have a chaotic state over there, and so the period doubling route to chaos is actually seen in this Lorenz model. So you start with hydrodynamics of bacteria, you have a steady state, you have a non-trivial steady state, you have a periodic state, and period doubled chaos, as you see over here. And then what? Then you can build up the gradient in the system, And now the point is that you have gone beyond the chaotic state, your gradient has become high, and it is what you are going to explore is the turbulent behavior. And what is important is that the turbulence now involves two fields, which is the phi. It is just technical. Instead of talking about phi, it is easier to talk about its gradient, which is this B vector over here. There is the Navier-Stokes equation, which now looks like this. This is the term which was already, here is the activity-driven term, a linear term from the activity and a nonlinear term from the activity. And here is the B, which is the concentration gradient being satisfying a diffusion equation. Here is the new system that we want to look at, and this has a conservation law which is different. There is the kinetic, the usual Kolmogorov term, which is V squared d3r over here, and now you see an additional term. So what flows from one scale to another is the conserved quantity over here. The conserved quantity over here is the flow, and this is very similar to what Pankaj and Mahendra and company used to do, where it was the heat, there was a kinetic energy and a potential energy which had to do with the heat transfer in this case. Here it is kinetic energy and the potential energy which has to do with the bacteria transfer over here. And obviously the transfer per unit time has two contributions. I take the time derivative. There is a time derivative coming from this BV dot and one coming from this BV dot. So time derivative of this part over here has to, and the question is who dominates? Well, if it is low activity, Kolmogorov does. The kinetic energy dominates. But if you go to very high activity, it would be the B which dominates. And now the Kolmogorov argument would have to be redone with the potential energy at the end of with the potential energy doing the transfer business. Predominantly, you do a dimensional analysis again. And what was k to the power minus 5/3 for Kolmogorov is now a k to the power minus 7/5. So you have this driven bacterial suspension, which is essentially, it seems, doing wonders for you. It is a system where you start out with steady state and then a periodic state, more complicated period double state, and period doubling taking you to actual chaos, and then you raise the activity still further, and in that we think it should be dominated by a Kolmogorov type of regime, except the scaling will now be 7/5 and not 5/5. So active matter seems to provide for the turbulence people solution, sort of way out for their unhappiness at not being able to. There were sort of bits and pieces of nice things here and there, not all of them coming in a single system. This active matter, driven active matter, seems to be a man for all seasons and gives you anything you want. Could be, I mean, too good to be true, but let's see what happens. Thank you very much. So I would be very happy to take questions. And, yeah.
So thank you very much, Professor Bhattacharjee, to giving such a nice talk and taking us to a tour of various fields and all the subtleties that lie ahead of us to address. And really we got a glimpse that why this field is still after working for 300 years, so difficult to understand because we don't have direct solution from the direct solution from the dynamical equation, and you can get that feel from Professor Bhattacharjee talk also. And I would like to quote Horst Lamb quote that he said that time that I am an old man now, and when I die and go to heaven, there are two matters on which I hope for enlightenment. One is quantum electrodynamics, and the other is the turbulent motion of fluids. And about the former, I am rather optimistic, and still I see that the quote is quite relevant. That you could have got it. So with this, I open the floor for questions and answers. So you can write your question on the chat box also. I would read for you. Or you can ask directly also. So please. Okay, so there is one question from Manas Kumar Rai.
Yeah.
If you are here, you can ask question directly. Manas? Okay, so his question is, what's the difference between chaos due to anisotropic diffusion and turbulence?
Chaos, as I said, is irregularity in time. So if I have a time series, the time series is going to be irregular and contain all kinds of frequencies in it. So that's the characteristic of chaos. Does not say anything about the spatial distribution. Turbulence has a spatial distribution which has to be determined by a probability distribution for the velocity field, as well as a complicated time dependence. It is turbulence is a problem with the PDE, chaos is a problem with the ODE.
Okay, so another question is by Sanjay CP. He asked this question, sir, is it possible to associate an effective temperature to the bacterial suspension?
Yeah, all right. People, the bacteria, people do that. It is a fair amount of literature on this effective temperature for bacterial suspensions. What I do not know that for us, we would like to maintain this bacterial suspension has been driven out of it. The temperature, of course, assumes some kind of a new equilibrium, but we are driving this bacteria out of equilibrium, and that, I believe, will sort of preclude the existence of a temperature in the driven system, which again is driven out of equilibrium so far as the bacteria temperature goes.
Okay, so any other question? So there is some comment coming from Professor Maheng Burma. So if Professor Burma is there, he can ask this question. Okay, so his comment is, Hop appears to be generic after supercritical pitchfork bifurcation, asymmetric rolls, oscillation in flow past the cylinder. So his comment is that Hop bifurcation seems to be quite generic in all kind of flow. So
yeah, that is true. I mean, that's the first instability is almost always a Hop bifurcation. That's true. The question is with the subsequent ones.
So can we make some assumption about that it is quite generic for such kind of flow?
I mean, I don't know any proof, but absolutely, Mahendra is absolutely right that, I mean, most of the systems that we know, the first instability after the steady flow is a periodic flow. So it's certainly the first instability is almost always a Hop bifurcation.
Okay. But in case of, I have just one comment here. In case of pipe flow, we get that without going to the Hall bifurcation, it goes to turbulent state.
Yeah, pipe flow is huge. Pipe flow is problematic. Sure, absolutely. Pipe flow does not have this, and the point with the see, all right. Why the pipe flow is so is different is because I have to worry about the flow is taking place primarily in, let's say, the Z, suppose the axis is the Z axis, and I have to be very careful about the radial direction boundary conditions. So these boundary conditions, when I have to pay a lot of attention to the boundary conditions, then this question of the hop being a generic instability is probably not, does not hold. So all those were, I mean, essentially infinite things extending out to infinity, and yeah.
So there is another question by Aswathi. So can you ask the question if you are here? MS Aswathi?
Yeah, I am Vishnu here. I'm sorry for using friend's account. Hi, it was a very nice talk. My question is, does the critical parameters connected to the transition to turbulence, whether it will change with the active matter?
Change from, yeah, it is, it's certainly, I mean, if I look at the convective fluid and look at the numbers of the Rayleigh number, which at which various things happen, the in the active matter business, those things are, if I all right, how do I scale things? If you look at the whole span of Rayleigh numbers over which interesting bifurcations take place, and the span of the equivalent numbers over here, this span is much smaller than the Rayleigh number span. So I think that is what is a great help, that a lot of bifurcations occurring in a small span of the driving parameter makes it easier for one to go through the whole sequence of instabilities without something else coming up and disturbing it. So yeah, I think that I'm not exactly sure whether what you wanted to know, but the way I would answer a question of scales would be in this fashion, that in the Rayleigh number, the scales of Rayleigh number over which I have to go through for getting into interesting regimes is much bigger than the scales in which this activity and the concentration gradient here has to change. Yeah. Things are happening over a much smaller range of control parameters.
Okay. What about the initiation of the turbulence? Whether it will be delayed or with the active matter? Initiation of the turbulence?
That that is actually I don't know the answer to that, because see, in driven active matter there is absolutely no experiments as yet. So you do have to have some feel for whether, I mean, when once, if one manages to set up this and get going without some experimental input on it, it is really very difficult to talk about. I mean, where one would be able to actually see the about the bifurcations. One can say that, all right, at the value of activity times the gradient having a value of 10 pi, this will happen, or at 15 pi, there's something else will happen, and so on and so forth. But when it is a question of where would the actual spatial flow become? That is very difficult to sort of answer unless one has a feel for experimental feel for the system.
Okay, thank you.
Another question again coming from Manas Kumar Rai. So if you are here, you can ask the question. Manas. Okay, so his question.
Okay, I'm just okay. Sir, actually, my previous question was different. Actually, now I have question that whether the inhomogeneous and anisotropic reaction diffusion system can be called as a turbulent phenomenon.
The inhomogeneous and the reaction diffusion system. Well, the point the if it all right, the basic difference between the standard turbulence, which I have been talking about now, and the reaction diffusion system is the absence of the advective term in the reaction diffusion system. All the all the nonlinear effects and the Kolmogorov kind of phenomenology has to do with the advective terms. It would have to be different in the reaction diffusion systems because of the nonlinearity there comes from the interaction between the different reactants. So that is concentration nonlinearity, and therefore the question. See the all right. Let me put it this way: the primary difference between that nonlinearity and the ones that I've been talking about is that in the diffusion-free regime, diffusion-free, which is no viscosity, no diffusion, and no external forcing, this system has a conserved quantity. The reaction diffusion system does not have a conserved quantity in that limit. So the universality classes of turbulence in them will be certainly different.
Okay, so another question is coming from Tanmay Banerjee. So if you are here, you can ask question. Tanmay Banerjee. Okay, so I can read his question. His question is, can hydrodynamic Darius-Landau instability or Taylor instability within a chamber lead to a laminar flow regime, to turbulence or chaotic regime?
What was the first part of the question?
So question is, can hydrodynamics Landau instability or Taylor instability within a chamber lead to a laminar flow regime, to turbulence? So his question is, the Landau instability or Taylor instability are responsible for the turbulence behavior in a chamber?
I don't know. I can only guess. The point is that if it is mixing, I mean chamber, I assume is a mixing flow. So if it is mixing flow, there would be, I mean there would be concentration, reactant concentrations in the chamber, or is this is this that kind of a chamber, or is it a chamber with just a single fluid?
Yeah. So it will depend upon the system, I think. So another question is coming from Arnav Saha. Arnav, if you are here, you can ask question directly. Arnav Saha. So Arnav Saha is asking question: in turbulent active fluids, what about the inertial regime? And then question is, in simple turbulent fluids, we have large length scales where energy is given to the system, and there is small scales where dissipation occurs. But in the active fluid, the energy is provided even at the small scale. So his question is that in active turbulent fluid, what will be the inertial range? How can we define that?
Oh, yeah, sure. There is obviously there is the viscosity. The small scale is still defined by the viscosity and the diffusion coefficient for the concentration for these bacteria or whatever they are. So that diffusion coefficient would determine the small length scales. That's clear. The large length scales would still, I mean, if I have to have a steady state, there would still require the coming in of, I would still have to supply some amount of energy from outside to this system for because the bacterial interaction is not at least the stress that we have written down is a part of a conserved quantity, and therefore is not contributing to the total energy increasing or decreasing. So the decreasing of the total energy is still done by the viscosity and diffusion. The increase is done by some way of putting it in. The coupling term is written as in a way, the coupling is constructed in a way that I have a new constant of motion, which is the usual kinetic energy plus quote unquote potential energy part. Yeah. So
Okay. Yeah. So Tanna Banerjee is just clarifying the things that he's asking that his question was for two fluid motion in a chamber.
In a
chamber. So
chamber with just one fluid.
Two fluids.
Two fluid.
Yeah.
Reactive or reactive, right?
Yeah.
So two reactive. I wouldn't know. I mean, the point is that the mixing between the two fluids would give rise to coupling between the concentrations would give rise to a nonlinearity, which I don't know what the result would be.
Okay.
Offhand, I wouldn't be
Okay.
able to say really.
Yeah. So any other question from audience? Okay, if not, sir, it was very nice talk, and we really enjoyed it, and we can see from the questions coming that is the beauty of JKV talk, that whenever he delivers the talk, people become intended to ask the questions at very basic level, and you can see that he tries very hard to give the answer at that level. So this is the beauty, and that's the reason that you find these followers across the generation, and we hope that we'll be having more and more this kind of time in future also to listen JKV at a different occasion. So with this, I would like Professor Basu to add few words about this call.
So first of all, thank you very much, sir. It's an excellent, introduction to chaos and turbulence and the soft matter physics. A number of people in our department are working. I mean, of course, Pankaj is the main person behind that. So it's really helpful for the entire department as well as Dr. Mishra's team. So we hope to have you here, sir, at some point of time when things improve, and we'll really want to have a set of lectures by you on a variety of things. and probably may not be all of you are aware that he has the full de Ferrel these calculations, etc. So are you still on with those?
No, that was, I mean, yeah, played around a little when Raka was a student with that, but yeah.
And he has an excellent book on statistical mechanics. So for the students, I think you should try to have a copy of the book. And I was fortunate enough to have a copy given by him, and I still have those, the soft copy of the book with me, and I heavily use it for courses. I mean, the courses that I teach on condensed matter. So thank you very much, sir. Thanks a lot.
So with this, we reach to the conclusion of this colloquium, and I would like to just mention that next week we won't have colloquium talk. Next week on 16th of September, again there will be talk by very eminent scientist of our India, from Indian soil, and that will be by Professor G. Bhaskaran on lifetime of the P.W. Anderson and the quantum matter. So he was a student of Professor P.W. Anderson, so it will be basically very interesting to hear about him. So actually laughing, I just, okay, he was not a student?
No, he was not a student.
He was collaborator, okay.
He was a collaborator.
Okay. So with this, I conclude the session today, and I thank you all of you to participating in the talk quite actively, and I also thank our technical team, Basab, Hemanto, and others for managing the technical part of the talk. So with this, I just say you goodbye. Bye.
Thank you,
Thanks
sir.
very much. Thank you.